time between now and the next lecture, just get onto Canvas and take care of that. I can't remember if I mentioned this already or not, but if you want some extra practice, there is an Ether nomenclature homework sheet on Canvas along with a key. So if you want to practice with that before you take the quiz, you can get some more experience with Ether nomenclature. You can check your work with the key and then go ahead and take the quiz. All right? Any questions before we jump back into things? All right, so let's go ahead and start with something here and get going. So looks like we're up and running. So where we left, oh yeah. Oh, sorry. That's better. Okay, so where we left off last time, we were talking about the reactions of ethers to the extent that there are any. They really don't do a lot with the bottom line. We talked a little bit about last time how you can oxidize ethers. When you oxidize the ethers, this is not ever something you really want to do. It's just something that happens, usually just over time with exposure to the air. The reason we never really want this to occur is because it makes those explosive peroxides and hydroperoxides. So it's something to be aware of more so than it is something that you're going to ever get in the lab and try to do. The other thing that can happen with ethers, so we talked about their oxidation. The second thing that you can do with these is you can cleave them under very, very strong acidic conditions. And this is not something you really generally set out to do either. And it will only occur under the strongest of acidic conditions. So you typically need something like either hydrobromic or hydroiodic acid. So not very common reagents. So it's not like you're throwing a little sulfuric acid as catalyst and then you're going to have to worry about hydrolyzing the ether. I mean, you really have to have very, very strong acidic conditions, unusually strong acidic conditions. But what can occur is, as you might guess, under these extremely strong acidic conditions, what's going to happen is the oxygen of the ether is going to go and grab the proton. And so what that will do is it's the same thing it does anytime you protonate an oxygen. You're just generating a good leaving group. And you have a good leaving group in the flask. You also have a good nucleophile. And so this will just undergo an SN2 type reaction. Where you make this pair. Now once you have the alcohol, this can undergo the same process again. So the oxygen can go and grab a proton from the HBr. Again, generating a good leaving group. And then the halide just comes in and kicks that out through SN2 chemistry. And so in the end, what you make is just two equivalents of the alkyl halide along with the loss of water. So not exactly something that is all that useful. Now you might say, well, wait a second, doing this reaction, we can generate alkyl halides, and those are useful reagents. and that's very true. However, if you're trying to generate an alkyl halide, there's much, much easier ways of doing it than subjecting yourself to HBr and HI. So this would be a kind of a crazy way of trying to go about making alkyl halides. All right. Any questions on these? So that's about it in terms of the reactivity of regular acyclic ethers. They don't do a lot, which is why they make such excellent solvents. That's why you typically use them primarily as solvent. What we're going to get into now, we're going to spend the rest of the chapter discussing, are the cyclic ethers. And this is kind of a unique class, and specifically with the three-membered cyclic ether, it does unique chemistry. And so we'll spend a bit of time talking about that. So I'm going to go ahead and give you some of the more common cyclic ethers. We'll first go over their names, and then we'll get into the reactivity. So the most useful cyclic ether, as I mentioned a second ago, is the three-member. And so this goes by a number of different names. You can call this simply epoxide. You can call it oxirane. You can call it ethylene oxide. But the IUPAC way of handling these cyclic ethers is it's almost like a cyclopropane in a sense. It's a three-membered ring, but to indicate there's an oxygen present, we just throw that in the name. So we're not going to call it cyclopropane to indicate there's an oxygen in the ring. We'll call it oxacyclopropane. And you can do that with any ring size. So for instance, the four-membered cyclic ether, we could call that oxacyclobutane. Now, these also have kind of older historic names, so that are non-IUPAC, kind of like the oxirane for the three-membered ring. The four-membered goes by a name called oxetane. Moving to the five-membered, we could call that oxacyclopentane. Its older historic name is oxalane. And then finally, we've got the six-membered. So oxacyclohexane, or the older way, oxane. Now, if you want, you can learn these older historic names. You still see them in use from time to time, but I'm not going to hold you responsible for them. All I care about is that you know the IUPAC way. So if I give you one of these types of compounds, these cyclic ethers to name, the only one that I'll be holding you responsible for are the IUPAC method. Okay? I do want to just look at one of these in particular. So this one is a very, very common solvent. You've probably seen it before, either above or below arrows in reactions. So its common name comes from this compound. So this compound is an aromatic compound that's called furan. And you can see that the five-membered cyclic ether, this guy is very structurally related to furan. In fact, it just has got an additional 4 hydrogens. And so for that reason, that cyclic ether, the five-membered cyclic ether, probably the most common way you'll see it called is as tetrahydrofuran, often just abbreviated as THF. So, yeah.
Wait, are you talking about the one above or the one below?
The one above, the one below, this one is furan, this one is tetrahydrofuran.
Okay. Is that one name we want to know?
I'm not gonna test you on it, but you probably have or will see it. It's very, very common, to do Grignard reactions or, LAH reductions in THF. Okay, so let's look at how we might use some of these names in order to name, one of the cyclic ether compounds. So they're very easy. Let's do something like this. So the only trick here is, when you're naming the cyclic ethers, you're always gonna start numbering at the oxygen. That's the only little trick to naming these. So looking at this cyclic ether, the one position will be the oxygen, and then you just follow the normal rules of rings, right? You can theoretically number clockwise or counterclockwise. In this particular case, I'm gonna be better off going in a clockwise direction because that's where I encounter my first substituent. So we'll number this guy around like this. Alphabetize the substituents, so we would have a 2-ethyl, 4-methyl, oxycyclo, that's a hexane. Okay. Any questions on this one? So I want to show you another example of that. Let's look at a 3-membered. So if we want to try to name this as an IUPAC in the IUPAC way, we would start numbering at the oxygen, so that would be the 1 position. And then whether we go clockwise or counterclockwise here, you're gonna get a 2,3 disubstituted compound. So in that case, that means we have to go to the alphabet, right? In this case, ethyl comes before isopropyl, so we would number around this way. And then, just following the normal rules, we would say 2-ethyl, 3-isopropyl, oxycyclo propane. Okay, so pretty straightforward. Does anybody have questions on how we did this?
Why is propane again?
Because it's a 3-membered ring. I mean, I know there's only 2 carbons, but the way these cyclic ethers are named is based on the overall ring size, not carbon number. So yeah, because it's a 3-membered ring, we call it an oxycyclopropane. In the same way that we did up here, this is a 4-membered ring, and we called it oxycyclobutane. So it's based on ring size, not necessarily carbon atoms. All right. Okay, so the last one I want to look at with you is what happens if you have a higher priority functional group. So for instance, what if we were trying to name this? So now we have a case where you have a much higher priority functional group. So we're gonna have to name this as an alcohol, which means that you have the epoxide as a substituent. And so in a case like that, according to the normal rules of nomenclature, we're gonna number this parent chain so that the alcohol gets the lowest possible number. So we would number it like this. To handle the epoxide as a substituent, it's pretty easy. We're just gonna call it an epoxy group. The only difference is you have to give both numbers that it bridges. So I'm not gonna just say 4 epoxy. Instead, I'm gonna say 4,5 epoxy because you have to give both of the carbons that it bridges. So we'll call this 4,5 epoxy. It's a 6 chain, so that'll be a X2E, 1 All. Alright, yeah.
If it were a different size ring, what do we call it?
You don't really see those
Okay.
very often, yeah. Okay, well, we're actually not quite done with this. So if you look at the epoxide has geometry much like a double bond. So do you see how if you kind of reference the epoxide here, you have a methyl group going kind of in a downward trajectory, and then the other carbon group going in an upward trajectory. So they're kind of going opposite one another. I could have had that in a different way. Look at the previous example. You see, can you imagine if you were looking at one of these epoxides kind of edge on, the substituents could either be both above the plane of the ring, or they could, one could be above and one could be below, right? So in that sense, we have to give stereochemistry in order to be unambiguous. And so for that reason, with these epoxides, it's very common to see either a cis or a trans with them. So actually, I didn't name that first epoxide correctly because I omitted the stereochemistry there. So to be absolutely correct, on that first example, I would need to include a cis. Similarly, in this bottom example, the one that we were just looking at, because the groups are going opposite directions from one another, to be unambiguous, we would need to say trans. Okay? Does that make sense? Does anybody have questions on that?
This is only for epoxides, right?
Yeah, just for the epoxides. Okay? Mm-hmm.
So is it just for epoxy, or is it like the carbons have to be right next to each other? Like, for the first example you gave us, they're about 2 carbons apart, right? So we wouldn't have to name cis.
Yeah, you really only see the cis and trans used with the epoxides. Yeah. Okay, then let's look, as I said, the epoxides are what we're gonna focus on. The rest of the cyclic ethers have a very similar behavior to just regular ethers. They're not very reactive, they're primarily used as solvent. The epoxides, however, have a unique reactivity. And I think you've probably already seen that. You probably got introduced to it last semester. You probably learned that you can do Grignard chemistry with these. So for instance, just as a quick review, if you had an alkyl halide, you could add magnesium to make a Grignard reagent, and then you could throw in ethylene oxide. And what that does is, remember the Grignard reagent is going to behave as if it were a carbanion nucleophile, and it's going to come in and it's going to attack and open up the epoxide, and what you make is now the benzene with a 2-carbon. Initially it's an alkoxide. Upon acidic workup, you get the alcohol. Okay. Any questions on that? Yeah.
Over on the left, is that a negative circle?
Yeah. Yeah. Because that's how the Grignard reagent always behaves, as if it is a carbanion.
So once it's gone, then it's the negative? Once the bromine comes off, then it's...
Yeah, so the actual mechanism involves the magnesium kind of inserting itself in between the ring and the bromine.
Uh-huh.
And because the metal is much less electronegative. That gives the metal a delta plus, and then the carbon a delta minus. And so that's why the Grignard behaves as it does. You know, it behaves as a carbanion type nucleophile. All right. Okay, so this should be maybe a little surprising. You know, for instance, let's imagine instead of doing this reaction with ethylene oxide, let's say I had just some other ether. Let's just do this exact same reaction. Could I do this? So, got that. I'm going to make the Grignard reagent. And instead of using the ethylene oxide, I'm going to use, let's say, diethyl ether. Could I do this reaction? So the exact same reaction that we just did with ethylene oxide, I'm going to try to do with this could we do that? The exact same reaction that I just did with ethylene oxide. Would this work? Do you remember last semester you did a Grignard reaction? Does anybody remember what solvent you used for the Grignard reaction? Diethyl ether. So obviously this reaction does not work because it's very common to do Grignard reactions with ether as a solvent. So clearly you wouldn't be doing Grignard reactions in ether if you had to worry about the Grignard reagent attacking the ether. So this reaction does not work at all. And the primary reason for this is, you know, we're attempting to do an SN2 mechanism here. Nucleophile attacking our supposed electrophile and kicking out the leaving group. Well, look at what your leaving group is in this reaction. You see how if we were to do this reaction, this hypothetical reaction as written, we're kicking out an O- leaving group. Well, think about the quality of that leaving group. Alkoxides are strong bases and thus very, very bad leaving groups. So that's the primary reason this reaction does not work. But what about above? Didn't we just do that? You had an incoming nucleophile attack and you kicked out what is effectively an O- leaving group. So what's the difference here? Why is it that we can seemingly have a very poor leaving group as an alkoxide here, but we can't do it down here? Think about it in terms of an energy diagram. So what we are trying to do in the second situation with the ether is we're trying to do an SN2 reaction where we kick out an O- leaving group. That is a very difficult reaction to accomplish because, again, your leaving group is so poor. Right, that's a very, very high barrier to overcome. The difference with the epoxide is its starting energy state is much, much higher. epoxide is starting up there. This energy diagram is gonna look a little funny, but. So why did I draw the starting material, the epoxide, so much higher in energy than the ether down here?
Is it because of the strain of the angle?
Mhm. Yeah. Remember, three-membered rings are very unstable, right? They have a high degree of what we call angle strain or ring strain. And as a result, the starting material energy is much higher with the epoxide than it is with the acyclic ether. And so when you're trying to think about doing SN2 type reactions on this, the barrier to overcome is really not that high given where you're starting from. So that's the real difference here. Mechanistically, we're not doing anything different. You have a strong nucleophile attacking a leaving group, making an O- leave. The difference is where these two starting materials lie energetically. Due to the ring strain, it's much higher energy, and so we can do this reaction where we cannot do it with other types of ethers. Mhm.
So if it's such a high energy, is it hard to mix the ethylene oxide?
They are endothermic reactions, but you can do it. So in fact, we'll see momentarily how you can do it. Okay, so the point is the epoxides don't react like regular ethers. And because they don't react like regular ethers, they allow us to do some pretty interesting chemistry with them. And that's what we're gonna spend the rest of, or at least the next 15, 20 minutes talking about. Number one, how do you synthesize them? And then once you do, how can we use them? All right?
Professor, so is that they're not possible at all, or is it just that energy required is not really realistic?
No, you can do it. Yeah, you can certainly make epoxides. That's what we're gonna talk about right now. How, if you wanted to use one, how would you go about making one? Let's talk about that. Let's talk about the synthesis of epoxides. So the first way I'll show you is the way that they're made industrially. Ethylene oxide is a very commonly used intermediate for a lot of industrial processes. And the way that they do it in industry, well, the way they do all of these, is through starting with an alkene. So we're gonna start with some alkene, and through a variety of processes, we can convert it into the corresponding epoxide. So the way they do it in the industry is they use oxygen as the oxidizing agent, and then they generally use some sort of a silver catalyst. It's not really the most effective way to do this if you're trying to do it on the lab scale, but this is how like ethylene oxide is made industrially. So let's talk about how you could do it in the lab. One of the ways of doing this is through halohydrin chemistry. So we're going to start with the alkene. And we're going to brominate it in the presence of water. And so this is a reaction you're very familiar with at this point. Mechanistically, what happens is the pi electrons go and attack the bromine. You make that three-membered bromonium ion, and then the water comes in to attack. And so as an intermediate, we're going to make this. So that's just the halohydrin reaction that you've known for a long time now. The way we're going to use this to make the epoxide is you add in a little bit of base. And to a certain extent, the hydroxide will deprotonate the alcohol. And then that very rapidly closes in to do that intramolecular SN2. Like that. Now, you don't, if you're gonna do this in the lab, this is all done one pot. So it's not like you have to do step one, this reaction, and then isolate this and characterize it, and then take it and do step two. This is all done in the same flask. So what you would do realistically is you would take your alkene, you would throw in the aqueous bromine, and monitor it by TLC. And so what you would be looking for is, presumably this would be much higher on the TLC plate than this. And so you would be monitoring it by TLC, and you would wait until this spot disappeared and you had complete consumption and a new spot developing lower on the TLC plate. Once you saw this spot disappear, then you would take and you would add in your base. And so it's not like it's a very tedious process, you just have to monitor it by TLC. In the end, you end up with good yield of the epoxide through this intramolecular SN2. Okay. Any questions on this one? Mm-hmm.
Then do you break it off, or do you just leave it attached to the ring?
It depends on what you're trying to do. Yeah, we're gonna see in just a minute how you're gonna use these, what the utility of the epoxide is. But before we get into that, I wanna show you a third way of making it. This third way of synthesizing them is actually the most common way. And that is through peroxy acid oxidation. So in virtually any organic chemistry lab, you have a very, very common reagent that's called metachloroperoxybenzoic acid. Nobody calls it this, everyone just refers to it as MCPBA. And if you think about it, you probably can figure out what this structure looks like. Because if you take the peroxy out of it, it's just metachlorobenzoic acid. So imagine that, okay? Metachlorobenzoic acid would look something like this. It's a benzene ring. We've got the benzoic acid part, and then metachloro. So it's just that. The whole peroxy thing, all that means is that you have an oxygen-oxygen single bond. So let me fix that. So that's metachlorobenzoic acid. The peroxy thing is just gonna be that. So in order to use this, again, we're gonna start with the alkene. And it's very simple. You just take MCPBA, usually use dichloromethane as solvent, and after a few minutes, out pops the epoxide. And just for the record, it's this, I'm gonna kind of highlight this in red. It's that oxygen that ends up getting transferred to the epoxide. All right. Any questions on that?
Do these work on a benzene ring, or?
You mean to try to, like, trying to epoxide the double bonds of benzene.
No, I mean like if it's on a benzene, right?
Mm-hmm.
It will just perform the same, right? There's no limitations?
Like if you had something like that?
Yeah.
Yeah, you could do that. It would be a little bit difficult, and this, not that you really need to know this, but in the real world, electron poor alkenes do not work particularly well. So if you were trying to do styrene, for example, that would not be so easy. And the reason for that is, mechanistically, the way the reaction works is you're relying on the pi electrons of the double bond to go and attack that peroxide bond. And so if you don't have very good electron density in your double bond, the reaction doesn't work well. And because you've got so much conjugation in here, these are not very nucleophilic electrons. And so the reaction doesn't work well. You pretty much need to have an isolated double bond for it to work well. Again, not that you really need to get that detailed in it, but just as an FYI. The other limitation, this one you do need to pay attention to, probably the biggest limitation for this is you cannot do this reaction where you have a ketone in the molecule. Okay, so for instance, if you were going to try to do push that down a little bit more. If you were going to try to do this reaction, it would not work. You end up getting this kind of interesting, weird rearrangement reaction. It's known as the Baeyer-Villiger rearrangement. But just be aware that you cannot use MCPBA if you have a ketone in your molecule. All right? Okay, so let's talk for a minute about why you might want to use epoxides. These are gonna, what I hope, you will start to use these quite a bit. Epoxides are a great way of building out a carbon chain and also introducing, they give you the option of introducing a great deal of complexity really in a single step. So for instance, let's say we were trying to make this. Yeah, let's do that. So if I asked you to do that on a synthesis homework or something, I'm sure you could do it. You know, maybe doing some Friedel-Crafts stuff, maybe some Grignard stuff. I'm sure you could figure out a way to do it. It'd probably take you quite a few steps, but I'm sure you could figure out a way to do it. With epoxide chemistry, I can shorten this to one step, maybe two if you include the synthesis of the epoxide. Because what it allows us to do is think about kind of breaking it like that. So using these epoxides in Grignards, I could make that alcohol simply by doing a Grignard between toluene and reacting that with that epoxide. Because remember, obviously in order to do the Grignard, we would need to have that as a halide, but that would be easy enough to accomplish just through benzylic bromination. But mechanistically, what's gonna happen is the same thing that happened using the ethylene oxide chemistry, right? You would make the Grignard there, that would be your carbanion nucleophile, and then this would come in and attack and open up the epoxide like so. And if you follow those arrows through, what you end up making is this very substituted alcohol. So the hardest part about using these epoxides is seeing them in the molecule, seeing them in the target, being able to look at this structure and say, oh yeah, I think I can do that with an epoxide. That's really the hardest part about doing these. Because the epoxides are very easy to make. You know, if I'm trying to make that epoxide, all I need to do is take 2-butene and treat it with MCPBA. But this, like I said, it can be a very powerful method of introducing a good bit of complexity to the molecule in a single step. So, any questions here on this before we continue on with it? Okay, so there's a couple things that we've got to get a little bit more nuanced with here. First off, notice in the epoxide chemistry that we've talked about thus far, namely using ethylene oxide that you've been using since 420, and also using this one here. Both of those are symmetric epoxides. So it didn't matter whether I drew the nucleophile attacking on that side of the epoxide or if it attacked over on that side of the epoxide, you got the exact same product because of the symmetry of the epoxide. But imagine for a minute if we had something like, I'm just going to do a generic nucleophile. If we have that. Does it make sense to you that depending on whether the nucleophile came in and attacked here, or whether it attacked there, you're going to get two different products? Can you see that? Does that make sense? So that would be a pretty poor reaction. You know, anytime you're doing a reaction and you're getting multiple products and almost equal yields, it's not going to be a great reaction. You know, if this were to proceed to give you 50% of the nucleophile attacking there and 50% of the nucleophile attacking there, that would not be a great reaction because you'd essentially be throwing away half of your product, which is never a good thing. So fortunately, we can predict relatively well how these reactions are going to go. And the answer to which one you get is really, it depends on your nucleophile. So, I'm going to divide, for this discussion, for the purposes of this discussion, I'm going to divide nucleophiles into two groups, strong and weak. So, for strong nucleophiles, when I say strong nucleophiles, I'm mainly referring to the negative nucleophiles. So things like Grignard, alkylithiums, alkoxides, hydroxides, those are the most common ones. For these, Steric's rules, meaning the nucleophile is going to attack the least hindered side. Okay, so for instance, if we were gonna do, something like that, there's clearly one of these two sides of the epoxide is less hindered than the other, right? It's gonna be a whole lot easier for that Grignard reagent to come in and attack there versus go in and trying to battle up against the two big methyl groups. And so as a result, the major product here would be that before acidic workup. All right. Any questions on that? Okay, so let's see the other situation. The other option would be if you had weak nucleophiles. So when I say weak nucleophiles, these are going to typically be the neutral nucleophiles, and there's not a whole lot of options here. Alcohols and water would be the primary ones. Now, this is something that we're going to see into the next chapter as well, and I think we've talked about it before. Reactions don't work when you have a weak pair. So if you have a weak nucleophile, you are not going to expect a good reaction if you also have a weak electrophile. A weak pairing does not lead to a reaction. At least one of them has to be strong. The epoxide itself in its neutral state is, I mean, it's an okay electrophile, but it's not particularly good. This reaction, it didn't matter because you had a very strong nucleophile in the carbonyl. So one of them was good, namely the nucleophile, and so we got a reaction. If you instead think about replacing this with ethanol, for instance, well, ethanol is not a good nucleophile. The epoxide is not a particularly good electrophile. You have a weak pair, and that does not lead to a reaction. So if we're going to try to use one of these neutral, weak nucleophiles, we're going to have to do something. We're going to have to do something to make one of them strong. And the way we're going to do that is we are going to use acid catalyst. Okay, because what's going to happen is if you throw in H+, as you could probably predict, the oxygen is going to go grab the proton. And so now, because we have a charged oxygen, this is a much better electrophile. So this is a weak electrophile. This is a strong electrophile. So now it doesn't matter that you're throwing a weak nucleophile at it because again, one of the two is strong, namely the electrophile. So if you throw in ethanol now, you're gonna get a reaction. But again, depending on whether the ethanol comes into attack here, or whether it comes into attack here, is gonna give you a different product. And under these conditions, it is no longer a sterically controlled thing, it is an electronic thing. So if you remember, think back to like the alkoxymercuration or the hydroxymercuration. When you have these charged three-membered rings like this, the positive charge, while I've written it formally on the oxygen, it's really kind of delocalized through the ring. And the bulk of the positive charge is going to be where it can be best stabilized. In this particular example, the positive charge is going to reside mostly at that most substituted position. So if I were to kind of try to quantify this in some way, I could maybe draw a delta plus there, but a delta plus plus there. Because there's going to be more charge developed at the more substituted position. And hence, that is where the nucleophile is going to attack. So following the arrows of this, I think what we would make would be, I'm gonna color code this a little bit, I think, because it'll make it easier to see, hopefully. We get something like that, where the blue came from the alcohol, the ethanol, and the black is from the epoxide. Does anybody have questions on that?
So if it was water,
Mm-hmm.
would that ether that you connected with just be an OH?
Uh-huh. Yep. So if and we can look at an example in just a second, but yeah, if we were to use water as the nucleophile, this thing would just be OH. Mhm.
What did you say the blue came from?
The blue is the ethanol, the nucleophile.
Okay.
So you could probably see, looking at these two examples that we've seen up to this point, one of these is much more useful than the other. This these guys are much more useful because it allows you to make carbon-carbon bonds, right? You can build out a carbon skeleton using the strong nucleophile situation. The only thing you can use for the weak nucleophile is, I mean, you're gonna make things like this, which are ether alcohols. You know, if you used water, you could make a 1,2-diol, which are great if you need to, but how often do you really need to do that? So, the point is, these are going to be much more useful and much more common than using the weak nucleophiles. All right. So let's see if maybe we can think about let's see if we wanted to do this. See if you could figure out a way of making that compound. what do we think? Could we make this with, epoxide chemistry in some way? I think we should be able to do this. Starting from that, if we epoxidize this, we would get that. And then would we be able to just throw in methoxide? Would that give us the product we're trying to make here? What do we think?
Maybe it's attached to the carbon that's tertiary bonded?
The tertiary one?
No, the one right, the other one, right
This-
between those two.
This one?
Yeah.
Well, that's what we would want, huh? Cause if the methoxide came in and attacked there, yeah, it would open up this way, and that would give us the product we're trying to make.
Then don't we need to use the acid catalyzed?
Yeah, exactly, that's the problem with this, right? I mean, if I had done this reaction as written, the methoxide would open up the epoxide, but it would go in, remember, we're dealing in this case with a negative nucleophile, a strong nucleophile. And when you're using that, Sterick's rules. And so it would be easier for the methoxide to come in like that and open up that way, which would not give us the right product, right? If we did that, take that to its logical conclusion, what we would end up making is that. Which is close to what we want, but not exactly what we want, right? Our substituents are in the wrong place. So to do this in the way that's gonna actually give us the product, yeah, we're gonna have to do this under acidic conditions. So using methanol under acid catalyst. And that would give you the target. All right. Any questions on that? All right, let's do one more and then we'll leave that for the time being. Let's do this way? Kind of, I think we actually looked at this reaction a minute ago. Would we be able to do the Grignard between the bromotoluene and this epoxide? Would that give us the right product?
I think so.
Yeah, what's the problem?
Well, the oxide doesn't have enough carbons on it to match up with that, right?
Let's count,
It
so
would put the-
excluding the ring,
it would
you have
put
one
the-
carbon there, 1, 2, 3, 4 carbons there.
It would put our OH on the end though.
Yeah, exactly, so one carbon there, 1, 2, 3, so we got the right number of carbons, the problem is the position of the hydroxyl group, right? So, remember how these work, you've got your nucleophile that's gonna come in and attack there, that opens the ring up that way. So your OH group in this case would be on that second from the farthest carbon, it would be there. So what do we do? Anybody come up with so that's not gonna work for us. Anybody come up with another strategy?
Did you have it just with an ethyl group and then nothing on that side?
Using acid catalyzed?
Could we do acid catalyzed here? Well, no, because even if we used acid, well, first off, you're not gonna be able to make a nucleophile because we're making a carbon-carbon bond, and you can't make carbon-carbon bonds under the acid catalyzed mechanism.
You would get an oxygen in there.
So what if we instead of using toluene, could we do this? Would that work? That would be the nucleophile. It's a negatively charged nucleophile. It's a strong nucleophile, so we're gonna get attack at the least hindered position. So attack would occur there, open the ring up like that, and I think, looks about right, huh? All right. Any questions on this? So the beauty of this epoxide chemistry, it can dramatically shorten your synthesis when you can see how to use it. Beforehand, I mean, we could have made this structure, you could have done that without epoxide chemistry, but you would probably needed to do like, I don't know, 3 Grignards at least. And here, we're able to synthesize that complex, highly branched alcohol in basically a single step. Okay, so it can really increase the efficiency of your synthesis, again, if you can see when to use it. And that's the hardest part with these. All right? Any questions on this?
Can you show us how you make that one? Because in the exam it says 4 carbon on the left.
Oh yeah, so that epoxide would come from presumably the alkene, like that, which,
That's 5 carbon.
yeah, so we would need to make that. So I don't know, there's a couple ways you could go about that, maybe doing a Grignard between those guys. And then, that would give you that 5-carbon alcohol with the OH group kind of in the middle. And you probably had to do some sort of some kind of an elimination to give you the Hoffman elimination product. So it's a terbutoxide kind of elimination to get the Hoffman rather than the Zyxis product there. All right. Any other questions on this before we move on? Okay, so the last thing that we need to cover before we end with ethers is a rather specialized class of ethers. These guys are known as the crown ethers. And they're macrocyclic structures. So the simplest of them looks like this. Like that. And the way we name these is you're going to give the total number of atoms in the ring, you're going to use the word crown, and then the number of oxygen atoms. So for instance, this one here, in total, the entire number of atoms in the ring would be 1, 2, 12. I'll use the word crown, and then the number of oxygen atoms in this are 4. So we call it 12 crown 4. And these have a very specialized purpose. And what they do is they complex metal ions. So for instance, what this guy would do if you had it in the presence of a specific metal ion, these crown ethers just trap the metal. And they do so through kind of these ion dipole interactions between the oxygens of the crown ether and the metal ion. And so different sized crown ethers can accommodate different sized ions. So this is the smallest of the crown ether, the 12 crown 4, and it, as you might guess, is going to accommodate the smallest of the metal ions. So 12 crown 4 would be used for complexing lithium. If you go up to the next size up from the 12 crown 4 would be 15 crown 5. And that's going to complex the next larger ion, namely sodium. And then probably one that's most commonly used is 18 crown 6. And that's going to accommodate the next larger ion, namely potassium. So who cares? Why would I ever need to complex a metal ion? This is more of a kind of a logistical thing. So imagine for a minute this. Let's say we were going to do a simple oxidation. Let's say we were going to do, I don't know, benzyl alcohol. And we're trying to oxidize this to benzoic acid. So Let's think about solvent choice. We're dealing with something that's got a big benzene ring. We're gonna probably need some sort of a rather non-polar solvent. So maybe benzene. All right, so we've got that dissolved. Now all we need is the oxidizing agent. So what could we use there? What's gonna oxidize a primary alcohol to a carboxylic acid?
KMNO.
Well, LAH is going the other direction. That's a reducing agent.
KMNO4.
Yeah, well, that'd be a good one. We could use potassium permanganate. Talked about that quite a bit. And therein lies the problem. Think about what potassium permanganate is. It's a salt. It's like sodium chloride, right? It's just instead of using the chloride ion, we're using a permanganate ion. But do you see why this might be problematic? We know that the benzyl alcohol that we're starting with, the reason we chose benzene is because we've got a we have a pretty good pairing there. Like dissolves like. You have a relatively non-polar solute and a relatively non-polar solvent. Like dissolves like, so that should dissolve well. How well do you think a salt is going to dissolve in benzene? It's not at all, right? I mean, an ionic compound you can think of as just a very, very extreme kind of polar. So you're talking about a very polar solute in a non-polar solvent. If you did this in the lab, if you took solid potassium permanganate, it's just a purple colored solid, looks a lot like iodine, and you threw it in benzene, it would sink like a stone and just sit there. And that's because the benzene cannot ionize or break apart the ionic compound. Well, that's a problem if you're trying to use permanganate as an oxidizing agent. If the permanganate ion is just clustered and tightly bound to its counter ion, then it cannot go and do any oxidizing chemistry. So what we would do in a case like this is we would throw in 18 crown 6. The 18 crown 6, remember what it does is it complexes the potassium ion. So essentially it's going to go in and strip away the potassium from the permanganate. And at that point you've liberated the oxidizing agent and it can go and do its thing. And you can see this quite dramatically. Like I said a minute ago, if you took potassium permanganate and threw it in benzene, it would sink like a stone and just sit as this purple colored solid surrounded by benzene. As soon as you chuck in 18 crown 6, the entire thing flashes brilliant purple as the permanganate gets dissolved because it no longer has its counter ion. So it's a pretty visually stunning thing to see. But that's where we're going to use these crown ethers. It's primarily used when you have a situation where you're dealing with an organic substrate and an organic solvent, yet you have to use an ionic reagent. It's just matching solubilities. All right? Any questions there?
So is it only because it's a metal ion being used in permanganate? So like, could we use like HNO3 instead?
Yeah, I mean, you could choose to use a different oxidizing agent, one that would dissolve better in the benzene. You could do that. But it just gives us options, right? It allows us the option of using an ionic type compound in an organic non-polar solvent. All right. Okay, any other questions on the crown ethers?
So, is it just when oxidizing or like at any time?
Anything, yeah, for any reason, anytime you would be using, an ionic type compound for whatever reason in the presence of a non-polar solvent, you could use these crown ethers. And what you tend to see is that it's just gonna enhance the yields. So, the reactions will usually work to a certain extent, but adding the crown ether will just push your yields higher. So that's normally the way it works anyway. All right, so I think that's probably a good place to stop. So I will see y'all in about 10 minutes, as we start.